Good morning, ladies and gentlemen. Yesterday, I wanted to introduce stoichiometry to you, and tried to do it via the little challenge game that you guys saw posted. Now, I was hoping you got some ideas out of that. Now, when you start up a challenge, what you're given is a chemical reaction. And what you're told is, like I said, you're going to be given one side, and the other side is going to be left blank. In order for you to make these adjustments, you need to base everything off of these numbers over here, this side that is given. What I was hoping you got out of this is that you started to realize that I've been using cooking analogies a lot, and I think it's the easiest way to understand this particular unit. So think of the chemical reactions as a recipe and read them out accordingly. So for this recipe, right? We need four NH3s. No, I can't write in this. Okay. Well, you need four NH3s and seven O2s. That makes four NO2s and six H2Os. Okay. So if you have four of these and seven of these, you're going to make four of these. Okay. And six waters. Okay. So that's how I want you to think about this. So let's look at what we're given. So products, look at this. So there's products and there's a leftover. Okay. So if you look at the products, it said we make four NO2s and we make six waters. Look at the recipe. This recipe already makes four NO2s and six waters. So all you have to do is follow the recipe. To make four of these and six of these, we need four NH3s and seven O2s. Okay, that's the recipe, and that'll make the 4 and the 6. Now, it says we have 4 NH3s left over, which means we have 4 extra NH3s that we don't need. And then you hit check, and you'll see that it turns out that that's the right answer. And I'll do one more, and then I'll start going to the presentation. That's, again, think of this as a recipe. 2 carbons and 2 waters makes one CH4 and one carbon dioxide. Okay. How many of each do we make? And look, so this recipe makes one of each, but we have 2 of each, which means all we need to do is double the recipe. If 2 carbons and 2 waters makes one of each, then we need to double how much we have. We need 4 carbons and we need 4 waters, and that'll make 2 of these. And we have nothing left over, so this should be correct. And it is. Okay. So that's the idea I wanted you to get out of it. So all stoichiometry is just calculations using these recipes to figure out how much of something we need. Okay. So stoichiometry is about measurements. Okay. So let's start with the presentation. Okay. So this is an example of when you would need to use stoichiometry. Okay. Airbags. Airbags are a safety mechanism in a car that activates upon a crash. Okay. How they inflate is via a chemical reaction. Okay. When you crash, something breaks. And when that thing breaks, it exposes a material to something else and creates a chemical reaction. And what that chemical reaction produces is gas. Okay. And this gas fills up the bag, and that's how you get your airbag. What you need to consider is how much of this gas do you need? Okay. How much nitrogen gas do we need in order to fill the bag so that it's soft enough to cushion you, but not too hard? Because if you make it too hard, then you're defeating the purpose of it in the first place. Okay. So this is an example of when you would need to use stoichiometry. And using those, and you remember the mole ratio with the volume. Okay, you want to fill it up to a certain volume, you got to use those mole calculations and Avogadro's numbers and things like that, and that's where all those other things come into play. Okay, so let's start off going through what we need. Okay, so here's a common chemical reaction. What you're going to need to be do what you're going to need to be doing is you're going to be converting one element amount to another. You're not transforming the element, but you need to figure out how much of something else you need. So, for example, let's say we have 5 moles of H2O. Okay, let's say we have 5 moles of this. I need to figure out how many moles of oxygen I need to use up those 5 moles. That's what you're going to be doing in this unit. Okay, so the equation gives you the recipe or the ratios, to be more specific. This is what the equation is for. So I just told you one way to read this equation is that 2 moles of hydrogen or 2 hydrogens and 1 oxygen make 2 waters. Okay, that's the recipe. 2 moles of H2 plus 1 mole of water yields 2 moles of H2O. I'm sorry. How you're going to set it up is in this ratio form. Okay. So I'm assuming you guys are all familiar with ratios and the term ratio and how they're applied. So from this one equation, you can get 3 ratios. It's 2 to 1 for oxygen and hydrogen. 2 hydrogens and 1 oxygen. That's 2 to 1. For hydrogen and water, every 2 hydrogens is going to make 2 waters. That's their second ratio. And for the oxygen, every 1 oxygen is going to make 2 waters. These are the 3 ratios that you get from that one equation. And this is what you can use to convert from one to the other. Okay. So let's get to an example. Okay. Here. So same equation as above. Okay. So the ratio we want to be using, in this case, we're going from moles of hydrogen, it seems, to moles of water. Okay. And we want to use this equation to determine how much water we are going to make. So what we need to do is first set up our ratio. First thing you do is set up your ratio. Okay, this is our ratio. It's 2 to 2. 2 waters per every 2 hydrogens. Second thing you do is multiply the ratio by how much hydrogen we have. We're going from hydrogen to water. Okay, we have 8 moles of hydrogen. We want to know how much water can we make with these 8 moles of hydrogen. So then the second step is to multiply your ratio by how much of the thing you're converting you have. Okay, and look at the ratio. Pay attention to the ratio. What's on top? What's on the bottom? You need to pay attention to the units. Okay, so when you're setting up these ratios, the thing you are converting to goes on top. Okay, notice how water is on top. The thing you are coming from goes on the bottom. Okay, notice how hydrogen is on the bottom. So that when you multiply these out, okay, remember that you can pretend that anything is a fraction. Okay, so this is just 8 moles of hydrogen. Okay, you can make that into a fraction. The reason I'm doing this is just to make what I'm saying a little more clear. Because when you multiply fractions, what do? You multiply straight across. So when you multiply this straight across, you're going to get a new fraction. And what's going to cancel out is this. The moles of H2 are going to cancel. And you're going to be left with just water. Okay? So that's why what you're converting to goes up top. What you're converting from goes on the bottom. In this case, it doesn't matter that much because they both have a 2 in front of them. The number is the same. But let's say this wasn't a 2 and this was instead a 4. Okay, if this was a 4 instead of a 2, then where you put them matters because you're either going to get 2 because 4 divided by 2 is 2, or you're going to get half 2 divided by 4. So then you can get the wrong number if you mess that up. Okay, so when you have it set up correctly, now you just finish up the math. After you set it up, step 3 is to finish the calculation. So if we multiply this straight across, you're going to get 8 times 2, which is 16, divided by 2, which is 8. So what this tells us is that 8 moles of hydrogen can make 8 moles of water. Okay? That's what this whole section is about. Okay, let's do another example. And this one we're going to do on our own from scratch. And this is the idea for today. So, given the equation, so it's the same equation as earlier. How many moles of oxygen do we need to react with 12 moles of hydrogen? So we have 12 moles of hydrogen. We want to know how much oxygen do we need to use up all 12. That's what that's asking us. Okay. So step one is set up the ratio. What are we comparing? We are comparing oxygen and hydrogen. This is what we're comparing. So since that's what we're comparing, we need to set up the ratio with that. Okay. So step one is your ratio. Okay. And this ratio is going to be between oxygen and hydrogen. What should be up top? What should be on top is what you are converting to. We want to go from hydrogen to oxygen. We know how much hydrogen we have, but what we want to find out is how much oxygen we need. So oxygen needs to go up top because that's what we're trying to find. Okay. So O2 goes up top, and then you look at the recipe, and whatever number is here is what you put next to the element. Okay. So in this case, for oxygen, it would just be 1. What goes at the bottom is what you are converting from. We are converting from hydrogen. Look at the recipe. The number that's in front of their hydrogen is 2. Okay. Now we have our ratio. Step 2 is to set up your equation. And that equation is how much you have of the original thing multiplied by your ratio. So in this case, we have 12 moles of hydrogen. And then we're going to multiply that by this fraction. And then after you got that set up, step 3 is to just multiply everything out. Okay, so 12 moles of hydrogen times 1, 12 times 1 is going to give you 12. And then divide that by 2, you get 6. Okay, so if you set this up, no, let me not put that there. Okay, you're going to get 12. I'm going to write out everything so you can see the cancellation. So you're going to get 12 H2, because you got to think about it like units. Okay, 12 H2O2 over 2H2. What happens to the H2s? The H2s cancel out, and you're left with just O2, and your final answer is going to end up being 6. Not 60. So let me be careful with that. 6 O2. 6 moles of O2. So if we had 12 moles of hydrogen, we would need 6 moles of oxygen to use up all the hydrogen. Okay. This is how you set up the stoichiometry calculations, and that's what this first section entails. This is the whole thing. Okay. And the rest of this is just nothing but examples of applying exactly that. Okay. So because the rest of it is examples, which you guys are more than welcome to look at, I'm going to do more from the actual worksheet, but the rest of this is more examples of doing exactly the same. Okay. So to not make this already pretty long, isn't it? Okay, we're at 14 minutes. I could go through the rest of these examples, but it's just us practicing that calculation over and over and over again. To prevent making this a 30-minute video, I'm just going to go straight to the worksheet and do some examples from there. Okay. So this is what you guys are going to be doing today. Let me zoom in just a little bit. Can I? Yeah. Okay. So this worksheet is divided into 4 sets. Okay. They have 4 sets. Each set, or as you progress through the sets, they're gonna add a new concept or a new element. Okay, element as in like, so right now we're just focusing on moles. Then we might add volume later. Like, see, they're talking about STP here. And as we go through the presentation over the course of next week, we're going to be adding more and more of these things. So that's how it's divided into sets. So set 1 just focuses on moles. Everything is moles. And then after that, you start to add more and more different things. Okay. So I'm going to go through C in number one. Okay. I'm going to go through C in number one. Pay attention to the wording. In A, it's moles and moles, right? But in B and C, it's grams and moles. Okay. So what's going on here is you're going to be doing the exact same thing we just did with the examples, except at the end you're going to convert them to grams, and that's what you learned how to do in the previous unit. Okay, when we learned about the moles, we learned how to go from moles to grams, grams to volume, and things like that. So we know how to do all. We theoretically know how to do all of this already. The conversions between grams to moles and things like that. Those conversions we know how to do. Now we're just practicing the stoichiometry. So let's go to C. C wants to know how many grams of oxygen we need to react with 200 grams of C2H6. So this is grams to grams, okay? Working with grams is difficult. So whenever it's asking you to work with grams as your final answer, step one is convert everything to moles, okay? So we want to convert all of this to moles first. And the only number we need to convert right now is this. So in order to go from grams to moles, remember that equation, N is equal to little m divided by big M, where little m is your mass and big M is your molar mass. So what we need is the molar mass of this. And the molar mass of this would be, what is that? Carbon is 12, so it's 12, 24. 24 plus 6 would be 30. Okay, so to convert 200 grams to moles, we would do 200 grams divided by the molar mass, with the molar mass being 30. Okay, this would be 30 grams per mole. Okay, that's the unit for molar mass, remember. So it's 200 divided by 30. Okay, 200 divided by 30 is how many moles we have, which comes out to be 6.66. Okay. So this, as a side note, this is 6.66 moles. Okay. So we have 6.66 moles of C2H6. Now that we have this number, we can start answering the question. Remember, step one is set up your ratio. What are we going from? Where are we going to? We want to go to oxygen. How many grams of oxygen? We're going to oxygen. So in our ratio, oxygen needs to be up top. The bottom, we are coming from C2H6. So C2H6 needs to go on the bottom of the ratio. And now look at the equation. What number goes with oxygen? 7. What number goes with C2H6? 2. Now that we have our ratio set up, now we can do the math. So step 2 is multiply the numbers out. So what is our starting point? Our starting point is the 6.66. And to save space, I'm going to stop writing the elements because I don't have that much white space here. So step 2 would be 6.66 times 7 over 2. And then step 3 is to finish multiplying everything out. So let me plug this in. I can't do that in my head. So 6.66 times 7 over 2, which is 3.5, is 23.31. So our final answer here is 23.31 0.31 moles of oxygen. Okay, this is moles of oxygen. This is not our final answer, but this is what we get from the recipe. Okay, this is not our final answer because they want grams of oxygen. We have moles of oxygen. Okay, and to get grams of oxygen, if you rearrange the mole equation, you get that little m is equal to little n times big M. Okay, so mass is equal to moles times molar mass. So we have the moles of oxygen. Okay, we have the moles of oxygen. We just need to multiply it by the molar mass. I'm erasing this so I can have some space here. So we have 23.31 moles of oxygen. And then what is the molar mass of oxygen? You might be tempted to say 16. It is not 16. One single oxygen is 16, but look carefully. Remember, oxygen is one of those things that lives in pairs. Oxygen is O2. So it is not 16, it is 32. Okay? So you multiply this out together, and this, you will get your final answer from this. So this is 745.92. Okay? That is your final answer. Okay? So to summarize, the chemical equations, think of them as recipes, okay? Think of the chemical equations as recipes. The recipe tells you the pairings of each and how much you make with it. So 2 moles of C2H6 and 7 moles of oxygen will make 4 moles of carbon dioxide and 6 moles of water. This is the recipe. If you follow this recipe exactly, this is what you're going to get, and this is what you're going to make, okay? If you follow it exactly. All we're doing in this unit is trying to figure out if we have X amount of one piece of the recipe, how much of the rest of the stuff do we need to use it all up, okay? That's what stoichiometry is all about. In this case, we're working with moles and grams, okay? When you're looking at the recipe, always work with moles, okay? So when they ask you to look for grams, that has to be a final step. So you need to work to do the calculations, the ratio, everything needs to be in moles first. And then if it wants grams, you need to convert it to grams at the very end, okay? So in this case, for part C, we started with 200 grams. First thing we did was convert that to moles, okay? So 200 grams of this element or this chemical, okay, is equal to 6.6 moles of it, okay? We divided that by 30 because that's the molar mass of that. That's where this came from. And then the rest of it is the same, your ratio, multiply it out, and convert it, okay? And then we have to convert it to grams at the end, okay? That's the gist of this entire section. For number 2, you have a similar thing. Look at part C, grams and grams. And then in B, grams and moles. And then A is just straight moles. So they try to increase the difficulty. In part A, it's just mole to mole, no conversions. In B, it's grams and moles. And then C, they give you nothing but grams. You need to convert things first. Okay. So to do part B, you can do the calculation normal, just when you find the moles of C2H6, just convert it to grams at the end, okay? So that is the gist of this section. And now I'll do one more example, okay? I'll do one more example from one of these, okay? I don't like that one. Let's do one. Do they have any? Let's do one more from here, okay? I like this one because this one's working with decimals, okay? You're not always going to be working with clean numbers, okay? How many moles of aluminum are needed to react completely with 1.2 moles of FeO, okay, or iron oxide? So we're given moles of iron oxide and we're comparing it to aluminum. So our ratio is going to have aluminum and FeO in it. But which one are we coming from? We are coming from the iron oxide. We are going to aluminum. So when we do step one, which is set up our ratio, the aluminum is going to be up top and the iron oxide is going to be on the bottom. Okay. Aluminum, the number 2, and iron oxide is 3. So this is our ratio. And then step 2 is to just multiply it out. So we have 1.2 moles of iron oxide. And we need to multiply that by 2 aluminums per 3 FeOs. Your FeOs are going to cancel. And then the rest you multiply straight out. So then this is going to be 1.2 times 2 Al, and this whole thing divided by 3, which is going to be equal to 0.8. Moles of aluminum. So to answer the question, if we had 1.2 moles of iron oxide, we would need exactly 0.8 moles of aluminum to react with it. Okay, these are exact numbers. In the future, you're going to see that we don't always work with exact numbers, which is why there is this leftover mechanic. The leftover mechanic we will get to eventually. We call that limiting or excess reactants. Okay, we call those excess. And one is limiting, one is excess. Your leftovers are your excess, and we'll get to that in a couple of days. Okay, but that's the gist of this section. Okay, that's the gist of this unit. Okay, so today you're just doing classwork set 1. Okay, so just finish off the rest of number 1 and number 2. Okay, and parts A, B, and C. Okay, this is what you're doing for today. Thank you all for your time. I wish you the best. Hope all is well. As always, if you have any questions, please reach out. Take care and enjoy the rest of your Friday.